showing to you my coding stuff. Is to give you some insight of the implementation. If you do not do implementation, then there is just theory. Computer science and cybersecurity is not theory. Someone may think, oh, computer science is a theory. Well, watch this. If you don't do any implementation, then it's useless, right? Even if you get a PhD degree in computer science and join, for example, Google or Amazon, if you don't know how to program, then they don't hire you at all. You know, although you invented brilliant breakthrough stuff, if it doesn't really give us a good impact, then it is nothing, right? Even mathematics give us something, right? Then why not computer science? All the engineering contribute somehow, right? If you do electrical engineering, civil engineering, then, for example, civil engineering, then they construct the bridges, right? Tappan Zee bridges. Look at the Tappan Zee bridges. Many of you are crossing the bridges.
I actually talked to a guy who works on the Tappan Zee bridge, and he explained to me why the crane came.
The work. All of your work. Okay? So, I want my students to do the project more seriously before the end of this semester. We have about a month, right? A little more than a month to go. So I want you to do, I think one of the requirements of this class is the project, right? I think the team project is required. So I want you to do some, James, can you look up the syllabus of this class if a team project is required? I believe so. So that you have to do the team project. So complete the team project and make it more seriously, not just to review literatures and compare and contrast. That is the first step for you to do some of the research work, right? And once you have some idea from the previous publications, then you need to improve one step further. Okay? Improve in theory and therefore implementation. Just a little bit. At least you can implement some theory already proven and published, well known. That is the minimum. Okay? Not for the purpose of the grading. Don't worry about grading. Okay? But really. Okay? I want you to expose. I want you to gain some skills and knowledge, and therefore you can deliver that to wherever you go. Okay. Okay. So for the homework, I'm going to give you a demo so that you may get some idea. This is a homework number 3, right? We already had that. Okay. Enter message 1. What was the homework? CSEC? Uppercase C and small SEC?
Yeah.
Marvin, you C. S. E. C. this is the signal that will be sent out all together. This is a multiplex already. So here, you know the signal. This is a 4 voltages, 0 voltages, 0 voltages, 0 voltages, whatever it is, right? So 4 messages. S. So what happens here is that 4 bytes, right? C6, right? 4 bytes. Those 4 bytes are spread out, but combined together. According to CDMA, the real code can. This is just voltage simulation. I'm going to close that. And see here, it is restored in this way. But if I follow that, message uppercase C is 01000011. That is uppercase C, right? And that is because our chipset is 4 bits, 1111. So in real implementation, yeah, 1111 is spread out. And also message spread out. I think we can see the message more clearly. So instead of 1 bit of 0, because our chip set is in 4 bits, so that is spread out. Message spread out. So 1 bit, 0 bit spread out. So 4 times, because we have 4 bits of the chipset. And next one can be spread out 4 times. And next 0 spread out 4 times. Next 0 again, next 0, next 0. And then 1 bit finally spread 4 times. And then and so on and so forth. And this 1111 accordingly spread out all, right? And then we made the exclusive OR. And then this is a message chip. Oh, wait a minute. This is a message for chip. And then we convert that into, I don't know, message for chip. So chip segment. Oh, this is for that. So we made this exclusive OR so that we have this. This is a chip segment from character C. We do that equally the same for other messages. So this is message from the second sender, so small s, and third sender send the message small e. Another sender try to send the message small c, all together. So we converted to voltage from the message 1, so message 2, and message 3 and 4. So we convert that into the voltages, and we add them all the voltages. So for example, first bits all ones. So if we add them, then it'll be 4, and then second voltages we have ones and zeros. Convert to, if it is 1, then we say 1. If it is 0, we convert to 2, -0, or the other way. If it is 1, then maybe negative 1, 0, then positive 1. It's up to your consistent algorithm and implementation. And then we send these voltages. So according to these voltages, we can generate signals. So send that signal out. The signals are spread out all 360 angles. If we have that type of antenna, right? Depending upon the antenna, you can reach further. Maybe there is a directional antenna, then it goes to one direction. Anyway, at the other end, there is a recipient. Receives these signals. And then using the same chipset that we used to, for example, for sender, then receiver use the same chipset. Similarly, second receiver will use the same chipset used by the second sender, and third and fourth. And then we, in the way that we do exclusive OR operation, then finally we have this, okay, convert that to binary code, and then we have the message restoration, okay. It's because one of you asked questions minutes before this class. So any additional questions? NumPy is used for only for the binary conversion. For example, if you have any character, how can you convert that into binary number? We do not look at the tables. Well, there's a fixed table, right? You can refer to table. The character, then it has a function called encode. Okay. So there are many ways that you can encode. ASCII code means it's not really 8 bits or 7 bits, right? That's for ASCII. 7 bits to use. But when you convert, there's another trick here. When you see the code here, for example, C, I start with a 0. If you make it the ASCII doesn't give you doesn't start with a 0. ASCII is the low 7 bits only. The upper 7 bits for other character. English alphanumerics does not need 256 different kinds of characters, right? 128 is sufficient, including all the special characters, all punctuations. So some of the tips that you need to do is that you need to add one. After you convert in ASCII, you have to somehow, in some other program, you have to do this. Add 0 if it is
Sorry, but that's
right. Like that, like this. I mean, all start with 0.
I found
If you have a 1, then it'll be it is not the alphabet that you understand. This is something else.
I found a function that would, in one line, change it into binary, but for whatever reason, the first character was always cut off.
Right.
It would either be 1 or 0, but
Yeah, therefore, you have to.
I had no definition.
Yeah, you have to add 1. Therefore, all the rest of the program can be consistently manipulated.
Right.
Because it, 8-bit for 1 byte. If you do that, then backward, if you want to have a binary coded to string, then you need to divide by
8. Therefore, you can convert that also. But anyway, that's a lot of a trick here. A lot of a trick in order to make this possible.
Right.
It's not a program.
But that's
it's
why
a trick.
That's why I'm asking if we could study your tricks to find out. It would, I think it would help out everyone here if we could go through your syntax, find out what tricks you're using, and learn. I know we're not in Python class.
No, it is just my trick only. It's not really known trick.
He can't tell you all the secrets.
I'm not asking for all the secrets. I'm just asking for
Enough to be able to do it.
Yeah.
And I don't know.
Okay, I'll think about that.
Okay. That's all.
Okay, let's go further. Carrier sensing. CSMA. In wireless communication, all the communication, Ethernet communication or wireless communication, we're now working on Wi-Fi. Okay. What we will do, I'm going to give you the broad idea about the materials that we are going to carry out in this semester. Mainly we'll look at Wi-Fi, which is 802.11. And then we'll look at cell signal, which is for your smartphone. And we'll look at cryptography, which is may not be covered, may or may not be covered in your 585 course. 585, they start with block cipher, right? So you have messages and want to encrypt the message altogether, and the keys, basically known, right? You don't have to worry about. It's not like a wireless communication. In wireless, you do not send data. You do not save data. You just send out, right? Which means that is a streaming data. So how can you encrypt streaming data? Not.
Well, that's why you have a temp file, temp folder. That's why you have a temp folder.
No, we don't do that.
No. That's why these have temps.
No, we don't. We don't. It is not. It's not the way that we do. Okay. No storage needed. Is that what you're saying, Cam?
No, the app data local temp, the folder, app data local in the temp. When you're streaming something out, you're sending it out to the internet, or when you're downloading something from the internet just for a quick look, it goes into your temporary folder and it clears out when you use the machine.
But that's not where the streaming encryption is. Is that what you're saying? Right? Or
Streaming is.
I
know what you mean by yeah.
Because I know
Right,
streaming
but we
is
do not-
posted somewhere and it's coming to your computer as fast
Maybe
as possible.
yeah, some buffering space needed, but not even any temporary storage needed. But anyway, that's what we are going to do. So two basic algorithms discussed. Wi-Fi. We're not going to do WPA or WPA2 encryption techniques. It is secure, right? A lot secure than WEP. WEP is already well known. So we look at the algorithm used in WEP, which is called RC4, right?
wait, so
RC stands for reversed. It's the name of a person who invented it. I think he's still in MIT.
so are we going over vulnerabilities of two, or just communications of WEP?
Encryption.
Encryption? We're going to go over encryption. And decryption?
Encryption and decryption, programming.
But why wouldn't we want to do it on WPA2 because it's not more common?
Algorithm is not publicly known.
I don't know that.
There's a reason it's not publicly known. Because if it's publicly known, that's easier to
People break in, but it's just through it's not through any kind of reverse.
It's not only key issue.
It's
Key
right.
streaming data. Key is instantly created. As we decrypt, we instantly create. So create the key, encrypt, and create the key, decrypt. So key is not the key issue in streaming wireless communication. We cannot share the key, right? When I call you, can I share? Hey, this is the key. From this point, you need to decrypt the way that I encrypt. Don't forget the key. We don't do that, right?
Right.
So key is not really the big issue. But anyway, that is a streaming encryption. So the RC for Wi-Fi. For cell phone, there is a algorithms developed also A/1, A/4, A/5, but we will look at A1/5 only. So all can be implemented somehow. Okay, but that is it. In Internet, Ethernet, if there is any error in communication, then carrier, because we have a media, we have a physical media line, right? For example, optical fiber. We have the line. The line can sense if there is a collision, right? That is what we mean by carrier sensing, multiple access. But in wireless, there is no sensing because there is no carrier. Well, actually, there is a carrier, right? There's just a signal. It's not the cable.
It's limited. There is a sensing, but it's limited.
Yeah, it'll tell you that it's not there. It won't tell you where it's.
It can be.
I want to pick up the MAC address of the computer that it's on, and it'll be like, if my computer tries to impersonate his without changing the MAC address, it'll be like, no, you can't see this because it's going to that computer.
That is the problem, right? Carrier itself cannot sense, so the device may be able to sense. Then he needs to send back another signal. Okay, that's what we learned the last week.
Right.
You missed, right?
You made class last week?
Yeah.
We didn't have.
Did you?
No, not last week.
Last week.
No,
you-
week before.
we had cybersecurity night. Yeah.
Were you here?
No, I
This?
had to miss it for work.
Yeah. This is what we did. I know you missed. 2 weeks ago.
I didn't miss class this
You
week.
didn't? Okay. That's what we talked
Right.
2 weeks ago. Somehow, so detection is not really ideal in our communication, wireless communication. So, which means the physical carrier sensing is not really ideal. Physical carrier sensing means in the physical layer, in the real cable, can any error along the communication be sensed by the carrier? No, right? In wireless. So virtual carrier sensing is the thing that we want to learn, which can be done on Mac, and an ideal one is the DCF for ITS, CTS, access mode, right? So we have, before we do this, okay, let's do this. DCF means distributed coordinating F4 frame. Yeah, distributed coordinating. As opposed to PCF, that is point coordinating, point-to-point coordinating. DCF coordinating has also RTS, CTS mode, or it has a basic mode. So we'll look at both ways that we can avoid the collision along the wireless communication. So virtual carrier sense has actually 4 packet types. Data that is one the message itself. That is a normal type, right? Normal data types. Data that we want to send. In addition to that, we have another types of packets. So RTS and CTS, request to send and clear to send. And by the way, we will have acknowledgement. So what happens here in the carrier sensing? For example, we have S for sender, and R for receiver. Okay, here, this is sender, this is receiver. So sender, not just sending the signals, but before it sends the data, there's 2 steps required. Sender one packet, so RTS packet, by saying that, hey, I'm ready to send. Then this receiver responded to that, hey, clear to send. So which means, yes, you can send to me. After that CTS, the sender can send out the data. And then finally receiver acknowledgement. So 4 different data packets should be shared, and therefore other neighbor A's and C's can avoid the collision. If they send the data at the same time, then at the receiver side or at the sender side there is a collision. That is the reason we do this. But it is not really, this slide explains, is it really a complete solution? It is not, but you can do somehow. So uppercase, if we have hidden terminal problems, then it can be resolved. But for example, this sender A here says ready to send. So B says, oh, clear to send. When B send out the packet, because this is a wireless packet, right? It send out all. It's not, CTS is not just sent to the node A. It can be spread out. It can be propagated all degree, all direction. So this guy C can also understand, can also receive the CTS packet. Therefore, C understands, oh, there's some transmission is going on, or at least B will receive data sooner. Therefore, this guy C back off, and so not try to send the data to the node B. Unless otherwise, C can send out and A also send out at the same time 2 data comes in, then there is only one antenna and there is a collision.
the gatekeeper, there's still a sequence, even if there's multiple.
No, it's not sequence. It is at the same time. The collision occurs at the same. It comes in the same time. Okay.
Even on the Wi-Fi level, it's still built on the logical level or the LAN level, right? So there's still going to be a collision.
Okay. The thing is this. Okay, I want to choose one. Then we lose the other. How can we handle the other messages that we dropped?
So they receive two. Okay.
Right? We cannot say that. Oh, hey, I lost this guy. Can you resend it? It's going to be work in Ethernet. It's not going to work in Wi-Fi, or not in cell.
We're talking about Ethernet right now.
Right. Wi-Fi communication. The other one here. Where is my mouse? Oh, here. So this node B wants to initialize to send the data. So the B says, oh, I'm ready to send it. So that packet propagates all around. So A receives it and C receives it, right? But actually B wants to send it to A. So A respond. CTX, oh, clear to send. So what happens here is that C does not wait to send since it does not hear A's CTS. C is the other side. C only knows that B wants to send data. C does not know who the person B wants to send out. Or only B knows that because B is the recipient. B knows that, A knows that A is the recipient. A knows that B wants to send the data to me so that A responded to it. So by sending CTS. But CTS doesn't reach to C, therefore C does not know. C only knows RTS, but no CTS.
It's going to be a collision then if he's trying to send.
So if C still send the data to B, then collision.
Yeah,
Still it happens.
clear to send.
Still it happens, right?
Yeah.
So still there's some collision.
That's what I
But a
was-
little bit of resolution, but still some.
'cause it's-
Therefore,
Yes.
we have some time space.
Because it's built into the OSI, even on the Wi-Fi level, even on the.
OSI is not. You're talking about Ethernet. You're still in 802.3.
No, but
We are now in 802.11.
Wi-Fi, it's still built on, like I said, it cannot work without the logical part, the physical part. It's not going to work without the physical part. And it's still built inside the architecture of the networking, or the 7 layers. It's still a part of the 7 layers, the Wi-Fi part.
Not
No?
wrong. That is
As far as-
Ethernet. That is Ethernet. It's not Wi-Fi. But anyway, so further down, Mac has some. It is currently implemented, so we do not have much data collision. Still, we have some data collision, right? When you access the Wi-Fi, then it's not 100% all the time successfully accessed. There's some loss. Still some loss. But improved a lot. So Mac has the capabilities, as you can see the screen. Mac maintains counters. So we have a short counter, long retry counter, and lifetime timers. Some timers, some number set, and then as node waits, number decrease. Okay. And then there is, as far as the number becomes 0, then wake up and see if I am ready to receive or I'm ready to send. If carrier is still busy, which means still used, then then back off again. But either back off or either sending out any type of packets, we need to have some time spaces reserved. Therefore, there's some time intervals. With that much, there's no collision. We'll see that in the diagram in the later slides. So here, okay. So we have a backoff counter and NAV, network allocation vector. This is vector. Vector is nothing but a counter. So it has numbers. I want to wait. Always that is binary exponential. It's not really binary exponential. Binary multiple of binaries. So 2, 4. Well, exponential, then 2, 4. No, 2, 4, 8, right? And 2 exponential. Whatever n here, right? So count 2, 4, 8, 16, 32, 64, 128, something like that. And also we have intervals. Remember that I said between packets, so we have acknowledgement packet, ACK packet, CTS, RTS packet, and also data packets. 4 kinds of packets should be nicely controlled. And also there is a backoff mode somehow. So during that backoff, times 2 ticks. That much we have to wait. Still in between backoff or any of these packets, we need some time interval. So this is IF means interframe. So we have acknowledge frame. Frame is nothing but the packet, right? Interframe between acknowledgement to CTS. Between acknowledgement packet and the CTS packet, between CTS packet, RTS packet, between RTS and data, between backup and other things. So interframe, IF means interframe. And okay, S means space, so interframe space. S means short, and P means PCF interframe space. D means DCF. This is distribute coordinate function. This PCF is a point coordinate function. So PCF, DCF, interframe space. This is the extended interframe space. There are 2 functions available, DCF and PCF. We are going to focus on, in this slide, DCF only. PCF is more like point to point. So not much collisions that we need to think. So it's not really. PCF usually used if there is a some mission critical deadlines, so that according to the priority issues, it's not for everyone, but we want to occupy this channel. There's PCF, point to point. This is the distributed. In the distributed coordinate function, was more complex, more complexity involved. That's what we want to learn. two kinds of functions, DCF and PCF. And also two kinds of mode. This is two media access mode and two different modes, whether it has infrastructure or no infrastructure, right? If no infrastructure, it is called ad hoc mode. We're not talking about here ad hoc mode. Ad hoc, then that is 802.15.4, yeah, usually 4. One, that's Bluetooth. Bluetooth is usually one-to-many, right?
Bluetooth is ad hoc.
Bluetooth is also ad hoc, but it's not really complicated ad hoc.
Yeah.
At all.
Isn't ad hoc not complicated? Isn't that the one that's like just want to get the connection going quickly?
And mobile, right?
Yeah, in theory, it is possible, but in real Bluetooth communication, there is a master and slave.
Right.
So master is always master.
Like,
So
your
it's
phone
multiple
is always-
slaves, and there is a connection is only one at a time.
Right. Like your phone's going to be the master in this scenario. and
Right.
Whatever. Bluetooth
One at a
device
time.
is.
So, which means it is not really complicated.
Complex
The
ad
communi-
hoc
yeah.
can have multiple masters, right? Multiple
So why that is infrastructureless mode? Because the connection topology constructed at one time and at another time there's a different topology constructed. So it is no infrastructure. But Wi-Fi, we have access point. Access point is always there, presumably. Okay, then we have some topology, structured topology. So that is structured. Because the AP stationed, of course there is the mobilized AP available, but still we consider that as a in this category, infrastructure. And we have, therefore, because of AP, we have SSID, right? Service set ID. We built that last lecture, right?
Yep.
Windows, we set up AP from your Windows systems. So SSID can come up, can be identified by your cell phone. Okay, so what happens here is that your network card use AP promiscuous mode, which means I want to talk to any. Is there any APs that I want to talk to? Promiscuous, okay? Doesn't matter. For example, when you turn on your laptop, promiscuously, it checks all possible APs. It doesn't look for, hey, I want to talk to this guy only. I want to talk to data link only. I want to talk to any specific router only. But it look for all, right? That is infrastructure mode. And then finally, you can filter that out. Then from that point, the infrastructure is constructed. So channel access mechanism, as we said, distributed coordinate function and point coordinate function. We look at only here DCF. And in DCF, okay, we have two modes available: basic access mode and RC access mode. Okay, RC access mode. So basic access mode is this. The algorithm is this. if we sense medium, we find out the carrier, medium, then we have to wait. For how long? DIFS time period. DIFS usually 50 microsecond. Okay. And so we wait DISF, and then still, and then there are two ways, right? Then medium. Okay. That medium either BG or not BG. So after DIFS, if medium is BG, then medium is not BG, we simply send out data. Okay? This is a basic access mode. We don't use it here any RTS CTS mode. Okay? This is basic. And if medium is BG, then we have to wait until not BG. But as we wait, we have to make a random backoff, which means as we back off, according to the random number generator, random number generates a binary exponential number. So it can give me, for example, hey, you wait 8 number, you wait 16 number, you wait 32 number. So I receive that backoff random number. So I have to wait that much. Why? Because medium is not available for me to use. It is busy. After that, still I have to do the same thing. Wait for DIFS and look for if any media is available. We keep doing that. There's another interframe spacing time. It's 10 microsecond, which is very short. It's right after the acknowledgement. Okay. So here is the diagram that we can think. This is one media, one same media, but pictorially we represent it in this way. At some points, here. Let's see very clearly. Okay, so up to this point, we know that that is BG, right? Then interframe, this guy did something. We do not know what it is, right? What it does, but maybe send the data. So we count from these points. So we start with the DIFS. So whatever the time period, we wait. And then right now, when we look, maybe channel is busy from this sender point of view. So this guy receives a backoff random number, which is 4 in this case. So random number 4. So it reduces the number by tick. Okay. So at the time 0, wake up again, and then to see if there is any media available. But fortunately, at this time, media is available. So this guy sends the data immediately, right? But on the other hand, this guy, up to these points, they have the same, right? But when this guy receives a lot longer backoff random number. I do not know what number that is. Let's say 8. This is a binary exponential number. So it tick that number to reduce. So when it wake up at these points, and the media is busy because the data is now being transmitted. So he cannot do but wait pictorially this is not really accurate, but somehow he needs to do again DIFS, as we looked at, right? DIFS, because that is BG, and then receive another backup random number and keep going. On the other hand, this guy, as it sends the data, and when the data is completely sent out, then we need to do short IFS, short interframe spacing needed. This is some time period. How long is it? 10 microseconds. And then acknowledgement. This acknowledgement to everybody, right? This is wireless. Everybody. So this guy also receives that acknowledgement. So this guy receives acknowledgement, therefore wait, DIFS. Every time we receive, we have to DIFS, wait. And then to see if the media, if there is a media available right now here, then this guy send out. He can send out, but somehow another backup in this particular slide. All right. There's a basic access mode, but another mode, a little advanced mode, is RC mode, which means we have ready to send and clear to send mode available, and there is another counter called the network allocation vector. This is a vector, is number counted. So NAV, network allocation vector, records prediction of the future traffic on medium, so that it gives us, for example, 16, number 16. Then we have to wait, we have to tick the counts. The counter counts down each time at uniform rate. So there's only one time clock, right? So 1 second is usually 1 second, the same amount to everybody. It's a uniform rate. Set based on duration field in received packet. So we have a RTS, CTS, and there's some duration, right? Because we do not look at that, but RTS and CTS, that is also packet. Therefore, for example, first 2 bits indicates what, and next 4 bits indicates what. So it has some structured the frames. So frame can be constructed. Here in this case, already constructed. That is standardized. RTS should contain that kind of messaging, or CTS another way. Data, there is a payload, so that you can send out data that you want. So when it comes to zero, then you can start with the RTS, CTS. When non-zero, then vertical carrier sense, then medium is BG, because there is none. This carrier sensing mechanism combines both mechanisms. Medium considered BG, or medium considered BG whenever either indicator carrier. Medium also considered BG whenever our own transmitter is on. So when I use, then I know my carrier is BG. Or by looking at, although I'm not using, because someone else uses, I can indicate the medium is BG. So BCF back off, here is an algorithm, right? 3 variables used, and frames, we have 4 kinds of frames, and an idea is similar to the others, right? We have a backup time here that is from 0 to whatever the binary exponents. If a medium becomes busy during back-off, the timer stopped and the new NAV is set. So it's a back-off another time. So similar to the other basic access mode, this explains when we use RC mode. Similarly, we start with a DIFS, DCF interframe spacing, and then if the medium is available, then this source here try to send out RTS. Okay. So RTS receives RTS send out. It's a spread out. It is a propagates normal. It is send out all direction. So destination receives it. Right? As it receives, then we have to wait. Short interframe spacing. So we have to wait short time, and then send the CTS. So destination says, "Oh, I'm ready to receive." CTS is sent out all around. Still, we have to wait. SIFS 10 microsecond. Although this sender receives the CTS, sender needs to wait that time period. And after that, sender now send data. After completely received, then destination still wait SIFS spacing, and then acknowledgement. Then this is done for one communication, right? Meanwhile, others, because this guy already know the carrier is busy, medium is busy, so this guy receives NAV, okay, network allocation vector, and then count down that. But when it comes to ACK receives, then still we have to wait DIFS. Everybody should wait DIFS. So after this DIFS, then to see if any one is available. Okay? If this guy says, "Oh, mine is available," then send out. Or back off if this is still busy. Okay? This is what wireless data can be transmitted wirelessly with no collision. It's not because collision is efficiently detected, but in this way we avoid collision. So we make sure that, oh, can I send? Right? Although what we have done so far, although we know how to make CDMA, for example, code division multiple access, like a direct sequence spread spectrum, the code that I showed, right? So multiple data can be multiplexed together, and then there is one signal to be sent out. So this is one signal. This data is not just where is it? Here. So this is not just one single data. This is a DSS, CDMA DSS. This is one signal. this one signal can carry multiple messages together. Still, we have another group of senders waits to use that. So that is the whole the scenario that we have been dealt with. Any question?
Yeah.
So next couple of slides. This slide explained another way, right?
Back on the infrastructure mode, a couple of slides back, I was wondering.
This is the infrastructure mode. What we are doing is infrastructure.
Okay, so on the nodes, you said the data transmit between the nodes of let's say the server and the client. So using network programming like let's say switch. I mean, does it use switch to communicate between nodes?
That if you see a switch, then that is 802.3. There's a physical. It's not wireless. There's no wireless switch. Oh, that's a good concept. Is there a wireless switch? I don't know. Sounds interesting, but there's no wireless switch.
Antenna.
Huh? Antenna. Maybe, yeah. That's Ethernet based. Ethernet based communication. Then there is the switches, routers, and
Yeah, the switch is before it turns to wireless.
yeah.
Right. Because you got the physical network, and then it hits the switch, and then it hits the router,
Mhm.
and then your wireless. Yeah, that's what I was saying.
So the second hits the router, it turns it's no longer 802.11.
Yeah, before, yeah, as far as it is Ethernet based communication, then that is 802.3. And after the wireless router or access points up in the air, then that is 802.11.
Second hits the router, it turns back to 802.3.
Correct. Yeah.
Yeah, the physical is 802.3, the wireless is 802.11.
This is sort of another homework assignment, but I'm not sure if I want to. For example, let's practice. We have slot time 1 and DIFS 3, SIFS 1. We have here time, right? Time, and we have station 1, 2, 3, 4. They're all wireless, and currently station 1 occupies to send the data, right? And this is RC mode, RC access mode. See here we have R for ITS, C for CTS. This is data. A for acknowledgement. So at the end of the completion of this data sending, then we need to do acknowledgement, right? But this acknowledgement between data packet and acknowledgement packet, we have SIFS. This is a short IFS time period, right? So acknowledgement done. And we start sending that algorithm, applying that algorithm with the DIFS, right? As we did so far. So DIFS, so whatever the number, we have to wait. So in this case, DIFS is 3 times the SIFS. Usually, in reality, DIFS is 50 microsecond and SIFS is 10 microseconds. So about 3 times or 5 times. It's no big deal, right? Microsecond, 5 times, 3 times. Anyway, short time. Right? And then And then where's my mouse? Oh, here. And then this guy says, oh, I'm ready. So R, C, and D. Meanwhile, all others back off. And then finally acknowledgement. And then the entire algorithm restarts with the DIFS. Okay. So whoever knows and find out medium is available, then R, C, D in this sequence. In between, we have SIFS, SIFS, SIFS. Meanwhile, all others back off. Okay, according to NAV, network allocation vector, which is nothing but random numbers.
How many microseconds are this?
10 to the negative 9. So we have second, millisecond, microsecond, millisecond, 10 to the minus 6. Millisecond and microsecond, and nanosecond is 10 to the minus 9. Right? Milli, micro, nano. Yeah, million. 1 millionth of second. That's a microsecond. A lot? No, very small. A lot means, yeah, I don't know what you mean.
How do they measure that?
How to measure? Our computer speed is a lot faster than that, so you can measure, right? Ours is gigahertz. Gigahertz means 10 to the power 9, right? Gigahertz means per second it can generate 10 to the power 9 pulse. One pulse is one tick. So it can count nanosecond. Our current process count nanosecond. So millisecond, you can count 1,000 times over milliseconds. Faster than that, maybe possible. We're talking about in real device, right? Supercomputer. The clock remains similar. Clock itself remains similar, but they right more process power.
Does it really count though, or does it run parallel?
Parallel, then more computation power, but time ticking remains.
Instead of sequentially, or is it all at once? Right?
That's a parallel, yeah. Okay, let's take a break, and when you come back, then we'll look at cryptography in wireless.
So this happens in 26 milliseconds or microseconds? The time on the bottom.
Oh, there?
Yeah.
It's all a microsecond. We're talking about microsecond.
Microsecond?
Oh, that's too short. Too fast, right? So SIFS usually 10 microseconds. Doesn't really matter.
It's fast.
Right.
Don't forget your wallet.
Why did I say that?
No, you mentioned something
No.
earlier, no?
No. You should not use a typical algorithm. Typical, it's different environment.
Right.
Therefore, all the cryptography is different paradigm.
Most people use WPA2 now. It's a standard.
Hmm?
And that's AES, right?
Yeah, advanced.
Can we AS for AIP?
WP1.
Okay. Where are we? So let's start with the basic stuff that, I mean, many of you already know this. I want you to recall and recap some of this. There are two types of keys, right? Public key and symmetric keys. Can anyone explain?
So you want us to explain public versus symmetric key? Public key is like
It's coming back to me, but
it's up to you. Just
Somehow, sorry, symmetric
key is
and
if we all
asymmetric
have-
key.
Symmetric key is if we all have one user account that we need to access something on, and then we enter in the same password to get the same material.
Right.
But if we're all on, say, a domain, and we have a file somewhere on a shared server, say Mark can't access it because he doesn't have rights, but you and I can, we can put in our own credentials to see that file, and we can see who edited that file last.
Symmetric is multi-directional. Asymmetric is one direction, one key to one encryption to one decryption.
Yeah. Yeah. So have you tried to generate symmetric key and asymmetric keys? This is very easy, right? If you can use OpenSSL, then you can generate keys, and also you can split public and private keys from there, and encrypt it and send it to someone else. That unless he has the other pair, then cannot decrypt. The description in this slide, it says the public key for encryption and private key for decryption. It's not really the case. I mean, key is a key, but the point here is that private and public keys are pair. So using one pair to encrypt, then the other pair can be used for decrypt. And symmetric key, on the other hand, the same key will be used for encryption and decryption. Algorithmic types. There are two types of algorithms: block cipher algorithm and streaming cipher algorithm. Block, entire or large block of messages can be encoded, usually using the same key, and also decoded. On the other hand, the streaming cipher, so a lot of partitions can be encrypted. Small chunk of message can be encrypted. So small block. So each block encrypted depending upon the previous blocks, because key can be continually generated and to be used. So how can we generate the keys? That is the issue, right? So RC4 is the algorithm that you can generate the keys. Streaming cipher to be discussed. By the way, next week, as I said, we have no class. James, do not come next week. Whole next week. I have no class because I need to go to Kansas City for CAE meeting. NSA CAE meeting. Huh? Okay?
I thought you were there last Wednesday.
Last week is for our event.
No, I know last Thursday was for the event. When was last Wednesday? I thought you were in Kansas City for that too.
NSA guy came here, so I need to take care of.
Alright, so Wednesday,
Yeah.
alright, and then you're going to Kansas
How
City.
can I come back Thursday if I am something on Wednesday in Kansas City?
Maybe you went by Tuesday and then you flew back Wednesday. I don't know.
I do not have a Trump airplane.
He doesn't have a clone either.
I do not have
No
airplane.
problem. So next week, no class.
I would.
We're all going to Kansas
Yeah.
City. So
So,
classes in Kansas City next week.
oh, you want to come? No. We have meetings Tuesday, Wednesday, and Thursday, Kansas City. And I'm going to leave Kansas Friday morning. So we do not have Friday morning class either.
So
Dr.
no
Chen?
Python either?
No Python, no 560, no 520, no nothing next week.
Just zero.
Dr. Chen is here though, right?
Huh?
Dr. Chen is here Tuesday? He's not going to Kansas, right?
No, he's not. Yeah. So,
The Kansas City is the NSA.
yeah, and that is center director meeting. Remember that in the United States, we have about 190 NSA Center for Academic Excellence in cybersecurity. We are one of those. So center director needs to gather together, and we discuss about curriculum. So what cybersecurity professionals needs to learn at the completion of their degree. So we need to
Very useful.
we need to maintain our curriculum up to date every year. So this year we will meet Kansas City. Last year we met San Diego. Year before Maryland, where there is NSA. And year before, every year we have a different location. Different location where there is some entities available.
I have the same thing.
Some security, national security organization is available. So all the city where we were going, there's some organizations.
We do the same thing with home inspection every year. We have a conference, the Society of Home Inspectors,
Okay.
and they do education through very similar.
So you tell us everything they tell you, right? You know that?
Yeah, we need 3 days. If I deliver to you everything that I hear from there, it's a three-day meeting.
Right?
3
So
days?
what you should do is you should record everything, and then we should just upload it while we sleep. We got this.
Just tell us what we need to know when you come back. They tell you.
Well,
Yeah, of course. For example, few years ago when we had the meeting, it was in, near Baltimore. At that time, many other universities already started thinking of software security, not the infrastructure security, not hardware security, not network security, but software security. How can we make our software secured? There are many ways, right? Not only to improve the performance of our code, but we need to make it secure so that software cannot be modified, manipulated badly. And how can we maintain the memory map securely? Memory, when you run any program, the program resides on our memory, and when that program runs against the data, then data comes in our memory. So every valuable assets available on the memory. So if somebody attacks the memory, then it doesn't attack our storage, it doesn't attack our network, but the memory, then we lose all the values, right? How can you protect it? That type of things discussed, I think, 2 or 3 years, since 2 or 3 years ago. That is the reason that we also developed the new course for undergraduates. We have two new courses recently developed, as I mentioned to some of you. Penetration testing and ethical hacking. which will be first offered in the spring semester. And then next fall, another course, Secure and Intelligent Programming.
Say again.
Next year, next semester.
Next fall, Secure and Intelligent Programming. That's for undergraduate.
It's for undergrad?
Yeah, not the graduate.
So we could have took it this semester.
It's a new course, right?
Yeah, new courses.
Yeah, I would have liked to take a penetration.
Dr. Young, question for you. How could you make, you mentioned it's a great idea, right? Securing the software because all hardware devices works with software, but as a hacker or a cybersecurity expert, you're going to get those software unless they're proprietarized and we don't have access to it. But as long as we're able to get our hands on it, then cannot we study the software and then being able to manipulate it from there? So how do you secure the software then? It's a great idea, but
Without having access to it?
yeah, you cannot secure the entire plethora of software in other words, without people like us.
The idea is this. When the college teacher teaches programming, they don't care from the beginning how to make it secure. For example, we want to store this data into that area. Then simply we simply teach, hey, use the variables and use it for this and that, and pass that data to another functions and receive that data. Whatever we do when you teach programming, our primary concern is the performance, right? Functionalities. Make it work. There is only one. Once it works, then we have to consider security. The second point is performance. Does it work efficiently? In one way, it takes 1 minute to complete the job. In another way, you can do in 1 second. There's a big difference, right? For anyone here, 520, for example, admin. We downloaded some of the programs, a priori algorithm programs, and run. So each program runs different. It takes different time. One of the programs is very slow, but my program can give me the answer quick, but the other program, it takes forever. Why? Because it is implemented in that way. So another second point of teaching programming is how can you make it more efficient? Can you make it? Can we complete it quick and use small space? Some programs use a lot of spaces. The really bad programs, when I was young, I liked it because it's simple to program. What is it? I'm always using database. If I use some and read in the database, I have all. So using SQL and whatever the value that I retrieve, I can retrieve and use it in my program and save it back to the database. That is worse, right? It cannot be used. It is good for you to maintain if there is no time critical issue at all, right? But for time and space issue, then database use a lot of space. Database takes a lot of time because of writing and reading and writing and reading. How can you make it more efficient? The third point, in addition to functionality and efficiency or performance, the third point is secure. How can we make our data secure, therefore no one can access it? That is very critical to
web program. Web. Because web may be available to everyone, right? So someone may enter whatever data they want, right? So from there, what if somebody, there's a text box, enter some script. Not the data, but script.
Will it work?
So your program receives that script. Immediately, if that script runs, then what happens, right?
No problem.
There are a lot of issues. So security. Intelligent. Program runs at time t, where at the time that technology is available. At time t2, so time elapsed, new technology comes up. You still need to run the same program. The same program will not cope with the new threats, new requirements. Yep.
But anyway, that is it. So let's go back to this.
I think
Okay, situation for wireless. Internal state is updated every other block. What I mean by that is, see here, key is not, we are not using a symmetric key, but we use, we are not using symmetric key, we are not using asymmetric key, but well, it is a symmetric key. We do not share the key. There is no time that we share in wireless communication. You could do that, but wireless communication itself, we cannot say that create public key, create a private key, and you need to share, therefore your communication or data can be securely transmitted. In general, it's okay, but it's not wireless technology. Wireless technology here is that it uses the same key to encrypt, the same key to decrypt. Only the issue here is that how can we change the key? Key can be generated automatically based upon the data, the nature of data itself, data that we want to send out. So depending upon the data, we can generate. So depending upon the data that we receive, we can generate and then encrypt it, decrypt it. Somehow, I'm giving you general idea. So situation here is that every small block data is not the same. Therefore, if we generate the key based upon internal data states, then key will be dynamically changed, right? Here. So from here to there. In between, therefore, we use a symmetric key cipher, and the key is state-driven and operates on the arbitrary message length, and an algorithm, cipher algorithm developed, RC4 and A5/1. RC4 is used for SSL and WEP. This is a secure session layer, right? A5/1 is for GSM. This is for cell phone. So we're going to use this when it comes to cell communication. There's a next module. And for this module, we will look at the RC4. RC4 is used for WEP. We are not going to learn WEP itself more the algorithmic approach, RC4. In general, cipher can be summarized in this way. Let's say we have a key. Which is K. And then initial state, this is state. Initial state I minus 1. Sigma I minus 1. Current state is sigma, I'm sorry, this is sigma I. Okay. So current state is sigma I, which is the function of previous states with the key that is applied to itself.
So it's sort of
Then that is the current state.
It's sort of like those wireless encryption techniques where you have to change based off the previous
Exactly.
zero.
Yeah, exactly. And the key stream is also generated by the current state. This is a key stream. Current state and previous key and current states, then we have key streams. So using this key stream J, if I have a message I, then we have cipher. This is cipher. And then this is encryption. And decryption can be done by the same key. So this is a symmetric key. Same key used for encryption and decryption. And that is applied to the cipher that we receive. Then we can restore the original message. This is original message MI, that is received by the recipient. That's the whole idea. Easy, right? Easy. Yeah. So I want you to implement this. I did implement many years ago. I can give you a demo also. Not today.
You can put it up with that Python script.
Yeah.
Yeah, I need to, because Evan requested. Here's what I'm going to do. I'm not going to give you, hey, is a bump. This is a complete set. I'm going to give you the major critical blocks. So based upon that, I want you to complete.
Okay.
Sounds good, right?
The web crawler.
Why are you talking about web crawler?
That's what you did. You gave us like little bits. And we had to get
He's talking about, I implemented so many other things because I like programming. What I did was that, given a URL, each web page, there is a anchor statements. So from that page, if you click, then it goes to another page, right? So can you do that automatically? Not manually.
Yes.
So read HTML files, bring the HTML into your program and scan and find out the external URL. Because you know the external URL, go there and bring that another the web page and scan again
Yeah, Sigma.
and go further back and forth. Then you can that is a web crawler, right? There's another stress. Okay, so this looks okay, right? Looks okay. But the problem here H and H prime, it's kind of an algorithm. How can we make this is the same key, right?
Mm-hmm.
This is a message data, input data. And in one way we have cipher, in another way we have original message. How can you make it? Number one, how can you make it quick? We do not have time. In wireless communication, if you turn on the cell phone and send out and receiver, immediately receive it. If it says, oh, I sent the message, did you receive? Oh, wait a minute, still decoding it. I'm still decrypting it. Doesn't do that, right?
With randomness, no? Is that an element of making it more efficient?
Another thing is here is bitwise exclusive OR operation. Bitwise exclusive OR operation. This is the key. Bitwise operation means it's not just a read bit by bit. In programming wise, it's just second. Not second, microsecond. If it is microsecond the processor, then it runs microsecond.
So
It's just a bitmap approach.
the yes or no, right?
Yeah. We call that self-synchronizing stream ciphers, which is this. So we use this, right? As far as we use bitwise exclusive OR operation, then same key, right? Same key. If I apply this at one time, I have this. If I apply at another time, then I have this. That's what it is. If I apply this again, the one more time bitwise exclusive operator, then that is cipher. If I apply to this cipher the same operation, then I have original message. If I have a message, then apply the same operator, then I have cipher. Back and forth, back and forth. Same operation, but there is a speed. There's a computer speed. If your computer is 2.5 gigahertz, then that is the speed of this operation. So we'll look at what bitwise operator is. This is 802.11. Used initially WEP, now advanced WPA and WPA2. And we have access points. So between your station, your laptop, and access points, there's a wireless communication. And that is encrypted in that way. So some ways of finding and accessing and associating described here, but we learned that in the previous module, right? We learned this. This is a summary. This is a recap of the modules that we learned. So I do not want to repeat this. Remember this we learned 2 classes ago. We learned that. Now let's stick to the cryptographies. Any data to be transmitted can be written in binary code. Question: what is the cipher speed in binary code? What is mercy? Now you know how to find it, right? This is for someone who do not know. So any data, any image, any video can be converted into binary code. So once you have a binary code, there's one thing. And also hash code should be understood. Hash code is based upon mod function, modulo, which returns the remainder. Whatever the number that you have multiple numbers. And you have a smaller set of numbers that you want to manipulate. For example, I can manipulate 1 to 5 only. In other ways, I can manipulate only 5 numbers. Then how can, given any numbers, doesn't matter the size of numbers, whatever the character that you send to me, I want to handle only 5 pieces. How can you do? You can use a modulo, which is remainder, right? You can convert any code, any text into binary, and then divide by the number. If you can handle 5 only, then divide by 5. Then remainder is the number that you can identify that one. So that is a hash function. For example, 17 divided by 3, what is the remainder? That's number 2, right? Who said 2? 2, correct. Why not 3? Because it is 2, right? Yeah, 15. 3 divided by 17, what is the remainder? 3. Right? 3 cannot be divided by 17, so the remainder is a 3 itself.
Smaller numbers is
It is a smaller number.
5.
So why modular or hash code is important? That is the question here. Because that's a non-deterministic in reverse engineering. If this is the number that I received, but I can manipulate only some of the numbers. But I can say, oh, I have number 3. You do not know how number 3 obtained because you have this number as input. Right? We do not know. Number 3 can be a remainder of any kinds of numbers that you can think, right?
You don't know which number they're using.
We don't know which number that is. Or we don't know which. Yeah, if it is divided by 3, then we do not know which number that is. Right?
You don't know the number that you're using either, right? You don't know the number that.
Although we know this.
Oh, you do not.
Yeah, we do not know. Although we know this is 17, we do not know. Number 3 comes from really number 3 or comes from number 20. Right?
Yeah.
There's so many numbers.
And there's different hashes.
Unlimited numbers. So that is non-deterministic. In real hacking, how can you do that? If we know this, then we can repeat. If you have programs,
Try all
so
the-
let program run.
All the possible.
Right, all the possibles.
And then one day later you have to try.
Yeah. That is the reason all the time we use prime number, right?
Yeah.
Rather than any number like that. 17, by the way, is prime number. But if we have any number, then it's easy to. There's a lot more possible numbers that we can match immediately. If it's a prime number, then it's very hard to reach that prime number. Any improvement dynamically. If you generate the key dynamically, then static hashing and dynamic hashing. See here, mod 3, there's a static, right? We fixed but mod 2 to the power n, then n increases.
It's using HMAC, right?
Huh?
HMAC.
HMAC. HMAC.
HashMac.
HashMac.
No, he's saying like
Something different?
like Mac, like computer,
Mac.
like
Not programming.
that's a kind of.
So in Python, there's an operator.
Hash-based method message authentication code.
Okay. Percent sign. That gives us the remainder. You can practice it, right? In Python. Any language. And another preliminary is bit operations, especially bitwise operation, exclusive OR.
So using the bit operation is one of the faster methods of.
Right. So if 2 bits are the same, then returns 0, different returns 1. So for example, if we have 1 and 0 and 0, then it returns 0. These two numbers, right? There's a known number, 0 and 0, or 0 and 1, because they are not the same, so it returns 1. And 1 and 0, they are not the same, it returns 1. 1 and 1, because they are the same, then it returns 0. That type of things, right? So can you handle this? Say these are the two numbers. We want to make an exclusive OR. You can make, right?
We had to.
One could be message, the other could be a key. Okay.
So one
Let's say this is a key. This is a message. And apply exclusive OR. Okay, whatever number that you would have. If you apply this again, exclusive number with the key, the same key, then you will get back this message. Practice.
So 0 becomes 1. From right to left.
What?
Um,
No, it's not that way.
It just means yes or no. It means like.
So let's do this finally, and then we'll stop for today's lesson. I'm going to bring this up here. Okay, I'll make big. Okay. I have here. What I'm going to do is I'm going to copy this, bring up here. And I have one more time. And I'm going to remove the first. Okay. So I have same size of data. Right? And insert. Is it text? Yeah, text. So what is the number? 1. I want to make this the same size to increase. Okay, maybe. Okay. So what is the next? 0 exclusive of 1. There's another 1. And 0 and 1. 1. 1 and 0, 1. 0 and 1, there is a 1. And then 1 and 0, there is 1. 0 and 0, there is 0. 1 and 1, there is 0. 1 and 1, there is 0. And
0, 0, 1, 1.
yeah, 0, 0, 1, 1. 0, 1, 1, 0, right? That is...
Yep.
This is too big. Oh, this is... Why this different font? Oh yeah, different fonts. So I'm going to change it to Tahoma.
Doesn't need to align perfectly. You got it.
Tahoma. Okay, so lined up. What happens here is that, let's say first one is the messages, second one is the key, okay? Second one is the key, and this is the cipher. So we send this. Instead of this first code, we want to send this. At the receiver side, it uses the same key so that we can have...
That would be a very simple cipher,
Okay. So let's put this here. Oh, I cannot. Let's see. Text. Okay. So, I want you to look at second and third only. So 1 and 1, so we have a 0. In this way, I could have Tahoma. And maybe increase 1, 2 more. Okay. So I'm going to line up here. And I want to apply the first and second and third line. So 1 and 1 means 0. And 0 and 1 means 1. And 1 and 1 means 0. 0 and 1 means 1. 0 and 0 means 0. 1 and 0 means 1. 1 and 0 means 1. And 1 and 0 means 1. And 0 and 0 means 0. And 0 and 1 means 1. And 1 and 1 to 0. 1 and 1, 1. 0 and 1, 1. 1 and 1, 0. 0 and 0, 0. What happens? Last and first, they are the same. Right?
Yeah,
Last and first, they are the same.
same key.
So what is the message? What is the point
So
here?
basically, if you do the third one and the first one, you get the second one, right?
Exactly. So exclusive OR operator, if we have the same key, then if we apply one time, then it goes to cipher. If we apply the same operator to the cipher, then it goes back to the original, and back and forth, back and forth, back and forth. So which is handy. It can be used in anywhere as far as we have very, very unique key, right? Messages is something that we want to encrypt. And the operation itself remains the same and very, very simple.
Okay.
Only the issue here is the key.
The key is
How
complex.
can we share the key? Can we share the key? Almost impossible, right? Because this is what it is. Then can we generate it? Or maybe so. Now how can you generate it? Generate it. Or generate the key based upon the data. Then we are talking about the same data.
The data, the
So-
time.
So although we don't share, but we end up having the same key. Therefore, at one side, encrypt, at another side, decrypt very nicely. We can secure the wireless communication. Okay, this is a basic idea, but in details will be discussed in 2 weeks.
Every time you share, you put it at risk too, over whatever connection you're sharing over.
That's how you can decrypt the key too.
Yeah, exactly.
That's how you can crack the key.